Number theory, lecture 5. And what we are doing is proving the fundamental theorem of arithmetic. So before I start on proving some of the lemmas that we use in the proof, let me remind you of the basic definitions and the statement of the theorem. So first of all, a prime number is an integer p greater than or equal to 2. A prime number is not 1, a prime number is not 0, a prime number is not negative. It's an integer greater than or equal to 2 whose only positive divisors are itself and 1 and p. And a composite number is an integer n, and it doesn't really matter whether I say n is positive or just any integer. I'm kind of curious how I defined it in the text. Let's see. A composite number is an integer n greater than or equal to 2 that is not prime. And in general, it's a hard problem to decide if an integer n is prime or composite.
Professor, what did you vote over there? A prime number is an integer p greater than or equal to 2,
whose only positive divisors are 1 and p.
Okay.
Again, I say this over and over. You shouldn't rely on my notes. You should be studying the text, which is legible, and my handwriting never is. But it's important to understand what I'm writing during the lecture. So prime number is an integer whose only positive divisors are 1 and p, and a composite number is an integer n, at least 2, that's not prime. So any integer from 2 on is either prime or composite. There's no third possibility. And if you have any experience with Maple, or even if you don't but want to learn Maple, there's a simple command in Maple to determine if a number that's not too big is prime or not. And let me just show you what that is. So I need to share the screen with a Maple window. So if you can see this, suppose we have a number n. Let's say n is equal to n is equal to, I'll just type in some big number. Now, that's the number n. You can't look at that easily and see whether it's prime or not. But there's a function called isPrime. And isPrime is a command in Maple. That's what's called a Boolean function. It outputs either the word true or the word false. So if I put in this number n, and we ask the question or we make the statement, n is prime, is that true or false? Maple says it's false. So even this number is pretty big, it's not a prime. That means it must have a factor different from itself in 1. Now, factoring an integer, the fundamental theorem of arithmetic says that every positive integer is a product of prime numbers in a unique way up to order. But to factor a number is also an extremely difficult problem. And extremely difficult means, in general, if you take a really big number, the fastest supercomputers in the universe won't be able to factor the number. But this number, even though it might look big to you, isn't really so big. And there's a command in Maple to factor an integer. The command is ifactor. The I stands for integer, so integer factor, ifactor. So now, when I enter this, it will factor this number, and lo and behold, this number is a product of these 4 distinct primes: 19, 139, 1097, 13001. I mean, to do this by hand would take forever. Plus, you never get it right because there's too many calculations to do by hand. You make mistakes. But this is an integer that is a product of these 4 numbers, and each of these is a prime. You want to make sure it's a prime. Is prime. Let's type in the number 13,001. Is this number prime? That statement is true. This is a prime number. So these two simple commands in Maple, is prime, which tells you whether or not an integer is a prime, and ifactor, which factors an integer. They're very simple commands, but they do a huge amount of computational work. Just to show that this isn't, Maple is case sensitive. You can't use capital letters is prime instead of lowercase letters. So someone start giving me digits of a number. I'll type it in and we'll see if it's prime or not. So unmute yourself and just give me some numbers. Anybody know a number? Don't be ashamed. Don't be afraid. I need to get a number. Anyone there? If you're there, type present in chat so I know that you're not just wandering away somewhere while your computer is on. So if you're there, type
Okay, I'll give you a number. You want me to give you a number?
Go ahead.
A big number or just?
And just give me some digits. I don't care what they are.
Oh, okay. 5, 2, 7, 8, 9, 3.
Yeah, keep going. It's too small.
Oh, okay. 0, 5, 7, 9, 9.
Okay. Is that a prime?
No.
No. Maple says this is not a prime. So I want to factor it. So let's see what the prime factors of this number are. Copy and paste. Put this number in there. What are the factors of that number? Wow. So this number, which is pretty big, is a product of 2 rather big primes. You know, if you wanted to know what the factors of this number were, you know it's not even. You don't have to divide by 2. You know it's not divisible by 5, because then it would end with 0 or 5. And you can check pretty quickly whether it's divisible by 3 or 7 or not, or 11. If you just do trial factorizations, dividing primes into this number one after another, it's not until you reach a prime, which is 60,733, that you get a factor. I mean, you'll never get that by hand. I mean, that's this. These 2 commands in Maple are just incredibly useful and powerful in number theory, and it's worth learning how to use Maple a tiny, tiny bit just so you can do this. Let's see. Let me save this in case I need it later. Okay, we're back. So the fundamental theorem of arithmetic says every positive integer is a product of prime numbers, and the product is unique up to the order of the prime factors. That just means if you take a number like 6, it's 2 times 3. It's also 3 times 2. But up to the order in which you write down the primes 2 and 3, it's the same factorization. So when you factor a positive integer into a product of primes, you get a certain number of primes that occur, and each occurs a certain number of times. And other than rearranging the order, there's nothing you can do that changes the factorization. And let me also just repeat what is also a very hard problem. Factoring an integer is too hard to do for very large numbers. I mean, the numbers maple will factor might look large to you, but is a computationally infeasible problem. No one has ever worked out a computer program that can factor a very large number. And people would get rich and famous if they could do that. And a huge amount of money is invested in this problem. And a huge part of our economy, of the global economy, is based on the fact that factoring an integer seems to be very hard. Okay, so if something is called a fundamental theorem, it's probably fundamental, and we need to learn how to prove it. And the first step is a lemma that goes back to Euclid 2,500 years ago. It's really a theorem, but it's traditionally called Euclid's lemma. And Euclid's lemma says the following. We have A, B, and C integers. So if A divides the product B times C, and if the greatest common divisor of A and B is 1, then A divides C. So A divides this product, but it's relatively prime to one factor, so then it completely divides the other factor. And the proof can be written like this. Because A divides BC, that means BC is A times Q for some integer Q. That's the definition of divisibility. And A, B relatively prime, the greatest common divisor of A and B is 1, means that AX plus BY equals 1 for some integers X and Y. So I have these two relations. This says A divides BC. This says A and B are relatively prime. So let me take this equation and multiply it by C. I get ACX plus BCY equals C. I just multiplied this equation by C. But BC is AQ. So I can substitute AQ for BC. Okay. I just replace BC by AQ. But here I have ACX plus AQY. I can factor out the A. This is A times CX plus QY equals C. And ABC, QX, and Y, these are all integers. So A times this integer equals C. So therefore, A divides C. Remember, this vertical line means divides. So that's the proof of Euclid's lemma. Any questions about this proof? This is a proof that you have to understand. I could very easily ask you to prove Euclid's lemma on the midterm. This is something that is basic in number 3. Then, what in the text is theorem 1.8 is a generalization of this as follows. Let me start it on a big piece of paper. This is theorem 1.8. Let K be greater than or equal to 2, and let A, B1, B2, B3, and so forth up to B sub K be integers. So the Euclid's lemma was the case K equal 2. So I have A in numbers B1, B2, which in Euclid's lemma I just called B and C, but here I have 3, 4, or 4 trillion integers, B1 up to BK. Now let these be integers. And if the greatest common divisor of A and B sub I is 1, for all I going from 1 up to K, then the greatest common divisor of A1 and the product of these numbers, B sub K, is also 1. So the theorem says that if A is relatively prime to several numbers, then A is relatively prime to the product of all those numbers. And the proof is by induction on K. It's certainly true for K equal to 2. For K equal 2, this is Euclid's lemma. And why is that? Let me just show you how Euclid's lemma for K equal 2 is exactly the statement. So suppose the greatest common divisor of A and B1 is 1. If A divides B1, B2, then by Euclid's lemma, what does Euclid's lemma say? If A divides a product and is relatively prime to one factor, then it divides the second factor. So then A divides B2. But we're given that A and B2 are relatively prime. So the only possibility is that A equals 1. And if A equals 1, there's nothing more to say. If we have integers A, B1, B2 up to B sub k, and if A is 1, it's certainly relatively prime to all these numbers because the only common factor of 1 and any other integer is 1. And so A is relatively prime to the product. So suppose, I should maybe just to make this a little bit more clear, suppose we're not in the trivial case, A is greater than or equal to 2. So A is relatively prime to B1, that's given. If A divides B1, B2, then A divides B2, but that means the greatest common divisor of A and B2 is A, but we're told that A and B2 are relatively prime. Right? It's also given that A and B2 are relatively prime, and that's a contradiction. So the case for k equal 2 is just an alternate formulation of Euclid's lemma. So let's do the inductive step. Suppose that k is bigger than 2. Suppose that k is greater than or equal to 3. And the theorem has been proven for k minus 1 integers, any k minus 1 integers, b1 up to b sub k minus 1. So if A and B sub I are relatively prime, for I going from 1 up to k minus 1, then by the inductive hypothesis, the statement is true when you have k minus 1 integers. So then A and the product of the first k minus 1 integers are relatively prime. But it's also given that A and BK are relatively prime. So this reduces to the case of just two integers, k equal 2. This is one integer, this is the other. So it follows that A and B1 up to B sub k minus 1 times B sub k are relatively prime. So that is a proof. And again, if you have not been required in other math classes to understand proofs and learn how to do them, this is a short proof, but there are a lot of ideas in it. And you may have to spend a lot of time, hours and days perhaps, just to understand this proof. But you need to invest the time. And I'm available before, during, and after lectures always to answer questions. But this is the proof of the theorem of this thing. And one consequence of this,
Are you gonna have a Zoom session throughout the week?
I'll have one tomorrow evening.
Okay, 7?
Okay.
Fine.
But not this weekend. Then I'll have Zoom sessions, a lot of Zoom sessions next week.
Okay.
But there will be one. I have to announce it or post it Thursday at 7.
Okay.
So this in the text, this is on page 26 if you're following in the text, which is not a bad thing to do. Theorem 1.9, which says if a prime number P divides a product of integers, then it divides one of the factors.
Hello, Professor.
Yes,
Hello, so I have a question. So all your notes is given in the textbook, right?
correct.
Okay, okay, okay.
Right, that is, I'm trying to follow the text, which makes it
Okay,
easier to study.
okay.
So if a prime number p divides a product, I mean, the examples I give, I just make up on the fly, like when I was factoring an integer at the very beginning of this lecture. You know, you give me a number, Maple will factor it. But the theorems and the proofs, I try to follow the text very closely, so then it's easier for you to follow when you're studying at home. So theorem 1.9 says if a prime number p divides a product of integers, it divides one of the factors. So proof. Suppose I have k integers, b1, b2 up to b sub k integers. Let p be a prime number, a prime. And suppose p divides b1 up to the product. So p divides the product b1 up to b sub k. If p is relatively prime to b sub I for all I, then p does not divide the product. That's the previous. And p does not divide the product. That's the previous theorem. So therefore, for some I, or for some integer b sub I, the greatest common divisor of p and b sub I is bigger than 1. But this is the greatest common divisor of p and b sub I. P is a prime. The only divisors of a prime are itself and 1. So if a number divides p and the number is bigger than 1, that means the number must be equal to p. Therefore, the greatest common divisor of p and p sub I must be p, which means p divides b sub I. P divides one of the factors. Again, because the only divisors of prime number p are itself and 1 and p. So if this number divides p and it's bigger than 1, this number must be p, which means p divides b sub I. So this is essentially what you might find in Euclid. It's a consequence of Euclid's lemma. And now I can prove the fundamental theorem of arithmetic. So this is theorem 1.10. Every positive integer is uniquely a product of prime numbers. Every positive integer n is uniquely up to order a product of primes. So there are two parts to this statement. Part 1 would say every integer is a product of primes. And part 2 would be the uniqueness assertion. that if you factor an integer into a product of primes in two different ways, you have exactly the same primes occurring exactly the same number of times, only they might have been rearranged when you write them down. Okay. So proof. Part one is quick to prove. Why is every integer a product of primes? Well, this will be proved by induction on n. If n is equal to 1, you would say it's a product of no primes. The empty product is defined to be 1. But if you start for n equal 2, n equal 2 is a prime. So how do you write 2 as a product of primes? 2 equals 2. It's a product of 1 prime. How do you write 3 as a product of primes? 3 is equal to 3. How do you write 4 as a product of primes? 4 is 2 times 2, and so forth. So the statement is certainly true for n equal 2, 3, and 4. And so let n be at least 3 and assume, this is the induction hypothesis, every integer strictly less than n is a product of primes. What about n? So consider n. We know if you take a number less than n, strictly less than n, it's a product of primes. So there are two cases. If n is prime, if n is a prime number, we're done. N is equal to n. That's a product of 1 prime. Suppose if n is composite, what does that mean? If n is composite, then you can factor it. N is equal to n1 times n2, where n1 and n2 are both integers strictly between 1 and n. If n is composite, it factors. It's a product of two numbers, n1 and n2, and each of them is less than n. By the inductive hypothesis, which says that every integer less than n is a product of primes, n1 is some product of primes, say p1 up to p sub k, because n1 is less than n. These are not necessarily distinct, but just a product of primes. And n2 is also a product of primes, say pk plus 1, pk plus 2, up to p sub l, product of primes. Therefore, n, which is n1 times n2, is p1 up to p sub k times p sub k plus 1 up to p sub l. This is just a big product of primes, so we're done. N is a product of primes. So this is straightforward. Every positive integer is a product of prime numbers. That's the first half of the statement of the fundamental theorem of arithmetic. The second half is the uniqueness. If I have two factorizations of an integer as a product of primes, they have to be the same. So let's prove part 2. So part 2 is the uniqueness. Suppose we have an integer n, which I can write in one way as a product of k primes, p1 up to p sub k. But then I have another factorization. I can also write it as p1 prime, p2 prime, up to p sub l prime. So here I have a factorization into k primes. Here I have a factorization into l primes. So I have to prove, first of all, that you have the same number of primes on both sides. K equals L. And these primes, these k primes, are simply some permutation or rearrangement of the primes p1 up to p sub k. Okay, so we have this statement. Here we have these two factorizations of n. So let's look at this. The prime pk divides n, right? That's what this says. And is a product of numbers, one of which is pk, so pk divides n with no remainder. But n I can write like this. So pk divides p1 prime, p2 prime, up to p sub l prime. So this prime pk divides this product of primes. But what did theorem 1.9 say? Here's theorem 1.9. It says if a prime number p divides a product of integers, then it divides one of the factors. So this prime number p, pk, divides this product of integers. So this means that pk divides one of these factors. So pk divides, let's say, p prime sub j naught, where j naught is some integer between 1 and l, divides one of these primes. And just to make the notation simpler, we can suppose that j naught is just equal to l. So we have pk divides p sub l prime. But these are primes. The only divisors of a prime are itself and 1. So if something divides pl prime, it's either 1 or itself. If divisible by a prime, prime is bigger than 1. So pk must equal p sub l prime. So if I have this factorization, pk, this prime must be one of these. I'll just assume by rearranging it's the largest one. So if this number equals this number, n divided by p sub k is the product of p1, p2 up to p sub k minus 1, which is also p1 prime, p2 prime up to p sub l minus 1 prime. Let's prove this uniqueness by induction. Right? So let's start off by assuming that uniqueness is true for every integer less than some number n, and now we want to prove it for n. So here I have n, it's a product of k primes in one factorization. It's a product of l primes in another factorization. But then I just showed that the prime pk must be one of these factors, say this larger one. So n over p sub k, if I divide by pk, I'm dividing out by pk, I get this equals this. This is n over pk. This is a number less than n. Just take a number, divide it by something 2 or bigger, so you get something smaller. It's a positive integer, less than n. And here I have a factorization in k minus 1 primes. Here I have a factorization in l minus 1 primes. By the induction hypothesis, k minus 1 equals l minus 1, which means k equals l. And these primes, p1 prime up to p sub k minus 1 prime, are a permutation, just some rearrangement of p1 up to p sub k minus 1. And that's the proof. That is the proof of the fundamental theorem of arithmetic. So for small numbers, you can try to factor things by hand. I mean, suppose you have n equal to 196. How can we factor this number? Well, you can always try and do a factor tree. Let's see. This is It ends in a 6, so it's certainly divisible by 2. So this is 2 times 98, I think. And this is still divisible by 2. This is 2 times 49. And 49 is 7 times 7. These are primes. So 196 is 2 times 2 times 7 times 7, or 2 squared times 7 squared. That's the prime factorization. In general, if you write n as a product of primes, they're not necessarily distinct. So you can, suppose you have k different primes in this group, you would normally write this as p1 to some power v1, p2 to some power v2 up to pk to some power v sub k, where p1 up to p sub k are distinct primes. So you write your number n as a power of primes, but you can collect the same primes and write it as a prime power. And we often denote by this notation v sub p of n, that this be the highest power of p that divides n. So for example, for 196, what's the highest power of 2 that divides 196? V sub 2 of 196 is 2. What's the highest power of 2 that divides this number is 2. The highest power of 7 that divides 196 is also 2. What's the highest power of 3 that divides 196? Well, you can think of this as 2 squared, 3 to the 0th power, 7 squared. That is, this number is not divisible by 3. So the highest power of 3 that divides n is the 0th power. And similarly, you could say v sub 5 of 196 is also 0. That's just another way of saying that the prime 5 does not divide 196. Any questions about any of this? Let's look at another example. Suppose I take n to be 25482,600. Factor n. Huh. That looks kind of hard. I could use Maple, but you also need to be able to do these things by hand for numbers that might not be too hard. You never know whether something is hard or not until you try to do it. Someone asked about whether you have to use Maple in the homework. No, you do not have to use Maple in the homework. I might give later in the term some extra credit homeworks that use Maple, but it's not required on any of the homeworks. Anyway, here's a number. God knows. Let's see. Is there any way of doing this by hand? Let me just try to factor it and see what happens. So the number was 25482600. I'll try and do a factor tree. This is clearly divisible by 100. So this is 100 times 254826. And 100 is 10 times 10, and 10 is 2 times 5. And along this branch of the tree, I can't go any further, because these are primes. But what about this? Well, of course, this is clearly even, because it ends in a 6. So this is 2 times, let's see, if I divide this by 2, I get 1, 2, 7, 4, 1, 3. Okay, so this is a prime, so I can't go further down on this left branch, but so I hope I did this right. Let's see. Well, let me just see if it's divisible by 3. When I divide 3 into this, I get 4, 2, see, 4, 3 into 12 goes 4. 3 into 7 goes 2, leaves a remainder of 1. 3 into 14 goes 4. 3 into 12 goes 4. 3 into 7 goes 2. 3 into 14 goes 4, and leaves a remainder of 2. 3 into 21 goes 7 times 1. I have, this is a prime, but what about this guy? Let me just try and, let me see what happens if I divide it by 3. So if I were to divide this by 3, this would be 1, 4, 1, 5, 7, I think. 3 7s are 21, 4 5s are 15, 17, 4, yeah. So this is okay. What about this? Is this a prime? Maybe it's divisible by 3 again. Let's see, if I divide this by 3, I get 4, 7, 1, 9. Oh, okay, so that's divisible by 3. I keep trying to divide by 3. Who knows what happens? I divide this by 3. I get 1, 5, 7, 3. Oh, wow, a lot of 3's in there. Okay. Should have had it written smaller or use a bigger piece of paper. Let's see, if I divide this by 3, 5, this is not divisible by 3. It's not divisible by 5. Let me see if it's divisible by 7. 7 for this goes 2. 7 to 17. No, it's not divisible by 7. The next prime is 11. If I divide this by 11, this goes in ones, 47, 143. Perfect. So this is 11 times 143, and I can tell that 143 is divisible by 11. This is 11 times 13. Oh, and those are both primes. Wow. So what I see when I mean, this is just one way to try and do it. I mean, any way that works, works. So this number, n, is equal to 2 times 5 times 2 times 5 times 2 times 1, 2, 3, 4, 3, 3, 3, 3 times 11 times 11 times 13. Wow. Let's see, this is, how many 2's are there? 1, 2, 3. This is 2 cubed. 1, 2, 3, 4. 3 to the 4th power. 5 squared. 11 squared. 13, which is the same as 13 to the 1st power. So this is the prime factorization of this number. And for this number n, V2 of n, the highest power of 2 that divides this number is 3. The highest power of 3 that divides this number is 4. The highest power of 5 that divides this number is 2. The highest power of 7 that divides this number is 0. It's not divisible by 7. The highest power of 11 that divides this number is 2. The highest power of 13 that divides this number is 1. And no bigger prime divides that number, so Vp of n is 0 for all primes p bigger than 13. All right, so just for fun, let me give you a chance to try and work out one of these problems. Factor the integer 31185. So I'm going to pause for a moment and give you a little bit of time, a minute or two, to factor this number. Write this as a product of primes. See what you get. Success? Anyone find the factorization? Yes. You can tell just by looking at this number, it's divisible by 5. So your first step might be to divide 5 into this number and see what you get. 6, 31, 1, 2, 8, 3, 15, 35, 7. So when you factor this, you will get 5 times 6237. Now this, not divisible by 2, not divisible by 5, so you might see if it's divisible by 3. If I divide 3 into 6237, I get 2, 0, 7, 9. So this is 3 times 2079. Let's see, is this still divisible by 3? I don't know. Let me divide 3 into that. 3 into...
Professor,
Yeah,
I have a question. So even the first one that you divide by 5, it can be divided by 3 as well. Like
Yeah. It doesn't make any difference what you try first.
okay.
I just said, when I look at that, the most obvious divisor is 5, because I just see the 5 there. So I just did that first. But if you want to divide by 3 first, it's okay. Because by the fundamental theorem of arithmetic, when no matter how you get this number written as a product of primes, it's always the same primes in some order. And here, 3, 2, 0, 7, 9, 6 is 18, 27 is 9. 9 is 3. So this is 3 times 693. This I can tell just by looking is divisible by 3. I can do that in my head. That's 3 times 231. I think this is still divisible by 3. 3 into 231.
77.
This is 3 times 77. And then 77, you just factor into 7 times 11. So this number is a product of 5, 3, 3, 3, 3, 7, 11. So what that tells us is that 31185 is 3 to the 4th power, 5 to the 1st power, 7 to the 1st power, and 11 to the 1st power. That's the prime factorization of this number. So V3 of 31185 is 4. V5 of 31185 is 1. V2 of 31185 is 0, because this number is not divisible by 2, and so forth. V7 of 31185 is 1. V11 of 31185 is 1. And for any prime bigger than 11, Vp of 31185 would be 0.
Okay, 5 equals 4. Wait, is that V2?
V2 of this number is 0. What's the highest power of 2 that divides this number? The 0th power. That's another way of saying that this number is not even. It's not divisible by 2.
But why you included 2? 2 is not on the prime list of this.
I felt like it.
Okay.
So, I could say, what is V101 of 3? It's just a question. What's the highest power of 101 that divides this number? The 0th power.
Okay.
Professor,
Yeah.
article so if you did not V2
I'm sorry. Your sound is garbled, so I can't.
3,089 to 0.
Sorry? No, I didn't understand what you were asking.
I'm saying if you were not to include V, I mean I don't know if that's correct, but V2 30,185 equals 0 and the answer is that wrong?
No. I mean, first of all, I didn't ask you to do this. I just asked you to factor the number. That was the problem. Factor this number. How does it factor? This is the factorization. This is the answer to the question. And then I was just using this as just to show you another example of what this notation means, what VP of n means. But the problem was to factor this. So if you factor this and get this result, you win. You solve the problem. This is just something else, something extra, something in addition. You don't have to do this unless this is what I asked you, but it's not. I asked you to factor this number. Okay. So this, everything we're doing today and what I'm going to do in the next few minutes is really fundamental number theory, stuff that you have to know. Okay, let's continue. What are some examples of primes? Two, 3, 5, 7, 11, 13, 19,
17,
29, 23,
31.
29. You get a lot of primes. And question, how many primes are there? You could ask, how many planets are there that go around the sun? Well, 7 or 8 or 9 planets go around the sun. How many primes are there? Well, maybe there are a trillion. Maybe there are a trillion times a trillion.
Infinite primes.
And you can go back to Euclid for an answer to this question. Euclid proved that, in fact, there are infinitely many prime numbers. There are infinitely many primes. Infinitely many primes. So as you start writing out the primes, you'll never get to the end. No matter how far out you go, there's an even bigger prime somewhere out there. And Euclid's proof is one of the classical proofs in all of mathematics. And we will show that given any finite set of primes, say P1, they don't have to be primes in order, just any finite set of primes, there still exists another prime. There exists a prime not in the set. So there can't be only finitely many primes, because if there were only finitely many primes, I write them all down, and there could not exist a prime that's not one of these. Okay? So this is actually a stronger statement, if you like, than there are infinitely many primes. It actually gives some way of bounding something. But this is what I'm going to prove. No matter what finite set of primes you give me, no matter how large it is, I can always find a bigger prime number or a different prime number. Actually, it's bigger for a different prime. And here's the idea. Suppose I let capital N, this is a finite set of integers. You can always multiply the numbers in a finite set, P1, P2, P3, up to P sub N. Just multiply these all out and add 1. So this is some positive integer. And it's a positive, not just a positive integer, it's a bigger than 1. So by the fundamental theorem of arithmetic, n is a product of primes. Every number bigger than n is a product of primes. So let a prime number p divide n. P divides n. But now, what can we say? So P divides n. But if P is one of the primes we started with, if P divides P sub I for some I between 1 and little n, that is, if P is one of these primes, then what can we say? Then P divides n, and it also divides P1 up to P sub n. We're given that the prime P divides capital N. If the prime P is one of these factors, is one of these P sub i's, then it clearly divides this. And if a number divides two integers, it divides their difference. So P divides this difference, n minus this. But n minus this is equal to 1. So this says P divides 1, which is absurd. A number bigger than 1 cannot divide 1. We have a contradiction. So therefore, P is not equal to P sub I for all I. So any prime that divides this number, capital N, is different from the n primes we started with. So that says, given any set of n primes, we can always find another prime not in the set. That is the proof. And again, this is a proof that you have to spend a lot of time, or as much time as it takes to understand. This you absolutely positively have to understand. Given any finite set of primes, there's a bigger prime. let's just look at some examples of the proof. So suppose I let P1 equal 2. Then N is P1 plus 1, which is 2 plus 1 is 3. This number is divisible by 3, which is not equal to 2. So if I start with this 1 prime, I get another prime. Suppose I take P1 equal 2, P2 equal to 3. Then N would be 2 times 3 plus 1, which is 7. And 7 is a new prime. It's not equal to the old prime. No matter what set of primes I start with, this product plus 1 is divisible by some prime, and that's a new prime that wasn't one of the ones I started with. And there's a traditional way of writing this. There's the function called pi of x, which is equal to the number of primes p less than or equal to x for any x. So pi of 2 is 1, because there's 1 prime less than or equal to 2. Pi of 6 is equal to 3, because what are the primes less than or equal to 6? 2 less than 3 less than 5 less than or equal to 6. I have 3 primes less than or equal to 6. Pi of 6 is 3. Pi of 5.1 is also equal to 3. It's 2 less than 3 less than 5 less than 5.1. What is pi of 10? So you look for primes. What are the primes less than or equal to 10? 2, 3, 5, and 7. So pi of 10 is equal to 4. And Euclid's theorem can be expressed as follows. The limit, we learned about limits in calculus, the limit as x goes to infinity of pi of x is infinity. As x gets bigger and bigger, the number of primes is strictly increasing. So just to make sure you understand the notation, compute right now, what is pi of 20? What is pi of 20 equal to? So this is the number of primes less than or equal to 20. So how many primes are less than or equal to 20?
Is it 9?
9. Let's see. So the primes less than or equal to 20, 2, 3, 5, 7, 11,
13,
13, 19.
17.
What?
17.
17, thank you. 17, 19. Anything else? See, this is 1, 2, 3, 4. So pi of 20 is equal to 8.
Oh, because I counted 1, that's why.
You know, right, right. So 1 is not a prime. That is the convention.
Oh, yeah.
A long time ago, some people thought you should count 1 as a prime, and other people thought you should not. And the consensus in the convention today, universally, is that 1 is not a prime number. The smallest prime is 2. So there's one more thing about prime numbers I'm going to prove, and I think just because we've already done quite a lot today, I'll put it off until our next class, which is the Sieve of Eratosthenes. And at that point, we will have finished chapter 1, and we will go on to chapter 2. But, and I've already posted several homeworks for the next few weeks. But all of this material that we're covering in chapter 1 is fundamental number theory. And you really should spend as much time as you can trying to learn it. Any questions before we stop for the morning? Okay. Let me just check the chat.
Yeah, I had a question, Professor.
Go ahead.
Professor?
Go ahead.
It was about the math lab. Have you spoken on that?
I'm sorry, a question about what?
Math lab. We don't have homework on that yet, still, right?
You mean Maple?
Yeah, yeah, maybe.
Yeah, no, there's no homework with Maple yet.
Okay.
And when there is, it will be extra credit. It won't be,
Okay.
yeah, there'll be extra credit homeworks. Okay, all. See you. The next class is next Monday. Bye-bye.